Hi, my name is Sebastián Alejandro Peña Rojo. My roll number is 2097163, and this is my presentation about semiconductors for the integrative learning product. First of all, what is a semiconductor? A semiconductor is a material that which has the main property that its conductivity increases with temperature. This conditional conductivity of electricity can be exploited to have an exceptional control over electricity and light. Semiconductors power modern electronics and computing, and they form the foundation of lighting, telecommunications, and sensing technology. The properties of semiconductors can be described by the band theory of conductivity. This theory describes solids as indefinitely large molecules in which molecular orbitals that are closely spaced in energy form an almost continuous band of energy levels. With this model, we can describe conductors, semiconductors, and insulators in terms of the bandgap, which is the energy between the highest energy band containing electrons, the valence band, and the highest unoccupied band, the conduction band. In a metal, there is no bandgap, which allows for the free flow of electrons, while in semiconductors and insulators, there is a bandgap, so there isn't that free flow. We can observe here two diagrams. The first diagram is for a metal. We can see that the S band is half full, so there can be a free transit of electrons. Meanwhile, in the second graph, the first band, the S band, is completely full, and the P band is empty. However, they are separated, so the electrons cannot move between one another. Intrinsic semiconductors uh, in In semiconductors and insulators, there is a band gap that doesn't allow for the free flow of electrons. However, in semiconductors, this gap is small enough that thermal motion allows for movement of electrons into the conduction band. This means that increasing the temperature of the material is going to increase its conductivity. We can see here in the GIF that as the temperature increases, the electrons move into the election band, creating a negative charge in the conduction band and a positive charge made by the positive holes left behind in the valence band. The conductivity, the dependence of conductivity on temperature can be described by an exponential Arrhenius-like equation. We can observe here this equation for the resistivity of a material, in which, as the temperature increases, the exponent for the exponential function decreases. As such, the resistivity decreases, and the conductivity, as it's inversely proportional, it increases. Apart from intrinsic semiconductors, there are also extrinsic semiconductors, which are semiconductors that have had impurities added in order to improve their conductivity. This is done through the addition of atoms that have more or fewer electrons than the parent element. Uh, and it only needs low levels of the dopant, only one atom of dopant per 10 to the 9 atoms of the host material. So this means that the host material must be extremely pure. There are two types of doped semiconductors. N-type semiconductors, which involve the addition of atoms with more valence electrons than the host material, such as phosphorus, which has one more electron than silicon. This provides more electrons that can jump into the conduction band. There are also p-type semiconductors, which involve the addition of atoms with fewer valence electrons than the host material, such as boron, which has one less electron than silicon. This creates positive holes in the valence band, to which electrons can jump into, decreasing the band gap. And here there is a graph in which we can observe, first in the A graph, there is an addition of a donor band, which is closer to the p band, the empty p band, and it can flow more easily into it. And there is also a graph for the p-type semiconductor, the B graph, in which an acceptor band is added, to which the electrons in the semiconductor can go into and shortening the band gap. Okay, for the production of semiconductors, the most important method for producing semiconductors is the Kokralski method, in which is used to produce bulk crystals. It involves the melting of the raw material in a crucible and the insertion of a seed crystal into the top of the melt, which is rotated and pulled away slowly from the melt. There is also the Bridgman method, which is similar to the Kokralski method, except that the temperature is controlled across the crucible, so that the temperature around the seed crystal is below the melting point. Here in the graph we can observe that there are two ovens, an upper oven and a lower oven, which control the temperature to be at dif- different amounts, different temperatures, and as such, laying it with control so that the temperature is lower where the seed crystal is introduced. And finally, another commonly used method is chemical vapor deposition. In this method, the gases containing the required elements are made to react in order for the element to be deposited into a substrate as a thin layer film. Here we have an example of a reaction utilized, which is silane, which would be the gas used to deposit the silicon, is decomposed by heat, and the silicon is deposited into the substrate, and the hydrogen is evaporated. Semiconductors are widely used because their properties can be easily modified through the addition of impurities, and their electrical conductivity can be controlled by applying an electric field, exposing to light, pressure, or heat. They have been used for transistors in bipolar junction transistors, which allow currents to be controlled by small changes in potential difference, which allows their use as amplifiers. And they can also be used as temperature sensors, as the current flow is affected by temperature. There are also light-emitting diodes. Semiconductors are used in photodiodes, in which exposure to light causes electrical conductivity to increase, and in light-emitting diodes and laser diodes. And they're also used in solar cells. Solar cells are made using the N-type and P-type silicon. When light strikes a solar cell, the electrons in the silicon are ejected, and they travel from the N-type layer to the P-type layer and then back to the N-type layer. This creates a flow of electricity. Finally, I want to talk about organic semiconductors, which are materials formed by organic molecules bound by van der Waals forces. These weaker interactions give organic semiconductor less electron mobility than inorganic semiconductors. However, they possess certain characteristics that can make them excel over inorganic semiconductors, such as their low cost and their low weight. Their optical properties have been exploited to make efficient organic light-emitting diodes and organic solar cells. These are the references I have used for this presentation, and that would be all. Thank you for watching.